So hello students, last class we have taught the introduction part of chemical thermodynamics, and in that class I have explained whatever the terminology involved in this chapter. Right now two important processes were remaining behind, that is reversible process and irreversible process. Okay, it's very important, that is reversible process. So what do you mean by what is this reversible process? So reversible process means if a system changes from one state to another state which takes infinite time. So it involves and you can say an infinite duration is there. Okay, it's a very long time, it's a very slow process, very lengthy process, but the key fact is whenever a system undergoes a change in state from one state to another state, then it has a tendency to again back into that particular path. That's why this is known as a reversible process. So here in thermodynamics, if I consider a system, so you just keep in your mind that our system is nothing but I have to consider a container like this, and in this container suppose a certain amount of gas I have taken inside this container, and it is well fitted with a piston. Okay, so reversible process means, so the gas is inside this container, that means it has some pressure, that is I can compare P gas, pressure of gas. Okay, so at the outside there is also pressure, that is external pressure, atmospheric pressure, you can say P external, that is external pressure. Okay, so here if I put a sand particle over here, sand, you know, it's a very minute particle, sand particle over here, then right now in this situation, before I lifted a sand particle over here, just see right now in this condition the P external, that is equal to P gas inside the container. That's why piston is here. So if I put a sand particle over here, that means I am increasing a very minute pressure over this piston. Then what happens? Then it seems to be the piston is just in that particular position, but what is the real fact? That there is a very small increase in driving force, or you can say external pressure. Suppose I need to compress this gas. Okay, I need to compress this gas, so I have to increase this external pressure over the piston so that the piston can move downwards. But reversible means I have to increase very minute amount of pressure over the piston so that the process becomes very slow. That's why I can write over here P external minus P gas, that is equal to dP, small dP, that is very small increase in pressure. So this one, if I need to compress it, then this one will be my driving force. So that means this driving force is infinitesimally greater than that of pressure inside the gas, very minute. Okay, now what do you mean by irreversible process? So irreversible process, again if I consider a container over here, that clear, and it is also filled with certain amount of gas, and the pressure, gas pressure, that can be represented as P gas, and it is well fitted to a piston again. Clear? So here what happens, this is P external, so again I can write P gas inside the container, inside the vessel, that is equal to P external, so that piston is right now equilibrium. Okay, so if I suddenly increase the P external pressure, that is driving force, if I need to compress it, then if I suddenly increase the external pressure immediately by putting heavy mass, let's say I am placed in this piston over here some mass I am placing over here, some mass, some big mass. Okay, so what happens? The piston, so initially let's say this one is volume V1, volume of the gas, then piston suddenly moves to here, you can say. So here right now this volume is V2. Clear? So but here if initial volume is V1, then the piston moves in such a way that to reach at V2, initially it was V1, then within this manner, then this one is V2, so it takes a long time to reach at V2. That means here this piston proceeds through lots of equilibrium stages, but here the equilibrium only occurs between the initial state and final state. Okay, so sudden change, that is a irreversible process, and infinite number of state of change involves a reversible process. And definitely in reversible process work obtained is maximum because it proceeds through lots of equilibrium stages. So I can compare for each equilibrium state W1, W2, W3 likewise. So here just add lots of work done is obtained, maximum work is obtained in case of reversible process. Particularly this is an ideal process, and such type of process is very difficult to realize. Okay, so in practice it is very difficult. So this one is ideal process, and but this one is a spontaneous process. Okay, so let us differentiate between ideal gas and real gas first, then we will proceed further. So now let's differentiate between reversible gas and irreversible gas. Irreversible gas. Okay, so first point, that is it is an ideal process. It is an ideal process and takes infinite time to complete. And here it is almost opposite. It is a spontaneous process. It is a spontaneous process and takes finite time to complete. Second point you can write, work obtained is maximum in case of reversible process, but here in irreversible process work obtained is minimum work is obtained in case of irreversible process. Next, a reversible process proceeds through several equilibrium stages, or you can say equilibrium states. Okay, while this irreversible process, there exists, it only involves a single equilibrium state, between the initial and final state. Then it is very difficult to realize. It is very difficult to realize. This one, it can be realized practically. It can be realized in practice. you can realize an irreversible process. But reversible process, such an ideal process, it is difficult to realize. So like that of in state of matter I have told you, it is very difficult to get ideal gas under certain conditions. Okay, but real gases are very common. So like that of here, reversible process is very difficult to realize, where as irreversible process is easy. Okay, so next we will discuss the theme of thermodynamics, you can say, that is internal energy. Internal energy. Clear? So it is designated as U. Internal energy means if a system is there, then whatever all types of energy that can be associated with the bulk of matter or in micro level also, you can say, all types of energy, sum of all forms of energy that is contained in a system or available in a system is known as internal energy. So most generally you can say, since we are considering the gaseous systems inside any container, so here system means you have to consider some gas enclosed in a cylinder and the cylinder is fitted with a piston. Okay, so in case of gaseous systems, the internal energy you can assume that is due to only kinetic energy, but it is sum of all forms of energy. I can write this internal energy, it is the sum of all forms of energy associated to a system. Associated to a system. That means I can say this internal energy that is equal to internal energy U, that is equal to, you can say, sum of potential energy plus kinetic energy plus electrical energy plus vibrational energy plus rotational energy plus translational energy, all forms of energy plus translational energy, etc. All forms of energy, that is called internal energy. Okay, now this internal energy, if I consider the system is in initial state having some energy U1. Okay, so suppose a system has initial internal energy let's say U1, that here, so after change the final internal energy of the system, that is U2, let's say. Okay, so what is the change in internal energy? Change in internal energy, that is del U, that is equal to final internal energy minus initial internal energy, that is equal to final internal energy minus initial internal energy. So that is equal to U2 minus U1, that will be equal to del U. This is the expression for internal energy. Okay, this is change in internal energy, U final minus U initial. So next we will see characteristics of internal energy. characteristics of internal energy. So internal energy is an extensive property since it depends upon the quantity of matter present in the system. So first point, that will be it is an extensive property. Internal energy is an extensive property. Clear? Internal energy is a state function. That means its change only depends upon the initial state and final state. It is a state function, or you can say it is a state property. It is a state function, and state function which depends on whose change depends only on initial and final state. Initial and final states. You can see del u, that is equal to u final minus u initial, or u2 minus u1. Next, its absolute value you can't determine. The absolute value of internal energy cannot be determined. However, the change in internal energy can be determined. Or you can say measure. This is the concept of internal energy. That clear? So again I have told you, for a cyclic process, since after several state of change, again it is back to the original state. That means the initial energy becomes final energy. So that the change in energy will be, internal energy will be 0. So I can write over here, for a cyclic process, the change in internal energy, that is equal to 0. Del u, that is 0. That clear? Because the energy at initial state becomes equal to the energy of a final state. That's why for a cyclic process, the change in internal energy is 0. Okay. Next, when a system undergo a change in state, clear? When a system undergo a change in state, that change in state appears due to change in internal energy. Suppose I am here, and if my state undergo change, suppose by change in any measurable property, if I undergoes from one state to another state, then that appears due to the energy change between the system and surrounding. Okay, so particularly the change in state of a system is due to the change in its internal energy, is due to the change in its internal energy. Clear? And this internal energy change appears in two form, very important. That is the two form of energy. I have told you initially that the change in internal energy, the change in internal energy appears in the form of, first one important, that is heat, designated as Q, and work. So heat and work are the two forms of internal energy change. Okay, so internal energy change appears in the form of heat and work. So heat means, heat is a form of energy. Okay, it is a form of energy transfer, you can say. It is a form of energy transfer, both heat and work. Okay, so heat, suppose there is one hot body, this one is hot body, and which is in contact with a cold body. So what happens? So heat will transfer from hotter one to colder one. Okay, so the temperature, whenever the temperature of two systems become same, two body become same, here this one will be T1, here also T1. Okay, so whenever the temperature of two bodies becomes equal, which are in contact with each other, then the heat flow becomes stop. So that's why this is a form of energy transfer. And you just remember, heat, suppose this one is my system and I am providing heat to it. Okay, heat given to the system, that is heat given to the system, that is equal to Q, that is positive. So Q is given as, assigned as positive sign whenever certain amount of heat is supplied to the system. That means the process is, endothermic process. Endothermic process. Heat is absorbed. Heat is absorbed. Next case, that is opposite. Suppose this one is a system, and if system releases some heat to the surrounding, that is heat released from the system is assigned by negative sign, that is Q, that is equal to negative. Clear? And this process you know, that is exothermic process. Exothermic process. Is that clear? So this is heat and its sign convention in our chapter thermodynamics. If the process is exothermic, energy is released. If the process is endothermic, then energy is absorbed. Again, the change in internal energy also appears in the form of work. So work is also a form of energy transfer. First one, that is heat, I have already explained. Next, that is work. Okay, so change in internal energy also appears in the form of work. So again, you just remember, work done by sign convention. I am saying sign convention, work done on the system is assigned by positive sign. Work done on the system means, suppose you are a system and I am supplying you energy. So if I am supplying energy to you, then what happens? Your internal energy definitely increase. So if internal energy increases, then that will be work done on the system, that is positive. Again, work done by the system, that is assigned by negative. Suppose here there is a system piston is fitted to this cylinder and gas is taken in the container. Suppose this piston lifted upwards by increasing the gas pressure or by increasing the gas volume. So increase in volume, that is called expansion. So here work is done by the system, so W is negative. So if the case is reverse one, this one is one container and certain gas I have considered well fitted to a piston. Suppose piston moves downward so that volume decreases. I am considering compressed ion. The gas is compressed. So here work done on the system, W, that will be positive by increasing the upward pressure. Okay, so work done, that will be positive. So this is the sign convention. In case of a exothermic process, Q is negative, energy is released. In case of a endothermic process, system absorbs certain amount of energy, Q energy, that is Q is positive. But here this is regarding the work done by the system, that is negative, and work done on the system, that will be positive. So next we will discuss thermal equilibrium, or you can say zeroth law of thermodynamics. Okay, thermal equilibrium or zeroth law of thermodynamics. Thermal equilibrium or zeroth law of thermodynamics. So it states that if two systems are thermal equilibrium to a third system, if two systems are thermal equilibrium to a third system, then they are also thermal equilibrium to each other. Then they are also thermal equilibrium to each other. Clear? That means suppose this one is a system A, this one is another system B. Suppose they are thermal equilibrium to another system C. Let's say this is C. So A is thermal equilibrium with C, B is thermal equilibrium with C. Then definitely A and B are thermal equilibrium to each other. So this is called law of thermal equilibrium, or this is known as zeroth law of thermodynamics. Next, a very important topic. Okay, till now I have discussed some important terminology and also the different forms of internal energy, that is work and heat, I have already explained. But now it's very important, very important, you can say, that is first law of thermodynamics. First law of thermodynamics. Okay, this first law of thermodynamics, particularly if I suggest the scientist name, that is Robert Mayer and Helmholtz. Okay, it was given by Robert Mayer and Helmholtz. These two scientists have proposed the first law of thermodynamics. Okay, and it was completely based on human experience. Okay, it was no practical proof is there. It was completely based on human experience. Clear? Now we should discuss what is the statement of first law of thermodynamics. It can be stated in different forms. First one, that is energy can neither be created nor be destroyed. It only converts from one form to another, from one form to another form. Clear? So the total energy of the total, that is, you can say the total energy of universe remains constant. Next, what first law of thermodynamics suggests you guys that whenever one kinds of energy disappears, then exactly equivalent energy in some other form will appear. Okay, so next you can write the total energy of an isolated system is constant. The total energy of an isolated system is constant. It can also be stated as it is impossible to construct a perpetual motion machine that can produce work without consumption of energy, Clear? So energy always remains constant. So here look at this point, it is impossible to construct a perpetual motion machine. That means if you consider your vehicle, then unless petrol cannot move, then you have to supply its burning fuel, then it will do work for you. So that is this point. It is impossible to construct a perpetual motion machine that can produce work without consumption of energy. Clear? Next, work and heat are equivalent to each other. Work and heat. That means if you supply certain amount of Q heat to the system, then definitely system will do some work by absorbing this heat. Okay, so heat converted into work in form of heat. Okay, next, that is first law of thermodynamics. In this thing I need to discuss its mathematical form. Okay, what will be the mathematical form of first law of thermodynamics? So next, that is mathematical form of first law of thermodynamics. mathematical form of first law of thermodynamics. Let's say a system is here, this one is a system, and suppose q amount of heat is supplied to system. So initially let u1 is was its internal energy, and if q amount of heat is supplied to the system, that means the system absorbs q amount of energy, and by absorbing, that means I can write here plus q, it absorbs. So let's say the work done on the system, that is plus w, work done on the system. So total internal energy of the system becomes how much? u1 plus q plus w. This is the total internal energy. So if I represent total internal energy, that is u2, so that will be u2 is equal to u1 plus q, amount of heat given to the system, and suppose w is the work done on the system, because you have provide heat energy to the system, so that energy should be used, that is used on work on the system, work done on the system, exactly, by absorbing q amount of heat to this system. So this u2 is final internal energy, so u2 minus u1, that is equal to q plus w. So I can write change in internal energy del u, that is equal to q plus w, where I can write work done on the system, where work is done on the system. So just think, if work is done by the system, then what can I write? If the work being done by the system, then the first law of thermodynamics can be expressed as, then del u becomes q minus w, because work done by the system, you know, that is negative. So this is the expression, mathematical expression for first law of thermodynamics. Is that clear? Okay. Now let us consider the special cases of first law of thermodynamics. That is, special cases of first law of thermodynamics. First law of thermodynamics. So for an isothermal process, just remember, for an isothermal process I have derived this del u, that is equal to 0, because internal energy depends upon temperature. That's why for isothermal process, iso means temperature constant. So once temperature is constant, del u becomes 0. So now substitute over here 0, that is equal to q plus q minus w. Okay, q plus w. Let's say this one. 0 is equal to q plus w. So that implies q, that is equal to, you can write over here q, that is equal to minus w. That is, if certain amount of heat is supplied to system and the system does not do anything, that's why the value of del u becomes 0, no energy change. So q becomes minus w, that is heat absorbed is equal to work done by the system. Work done by the system. Next, if I consider another special case, that can be, you think this del u is equal to q plus w. Am I right? Okay. So for isothermal process I've gone, and for, let's say, for adiabatic process. For adiabatic process Q is equal to 0. So del U is equal to W. That means work done on the system is equal to del U. Del U मतलब change in internal energy. That is W, work done on the system, is equal to the increase in internal energy. Clear? So this is the conclusion of first law of thermodynamics. Okay, so there are few other special cases. Is that clear? So that I will discuss in my next class. Okay, thank you.